He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Hello.
Richard Faull here.
Kim Hill here. How are you?
Oh, I'm good, thank you. Lovely to talk to you after so many years.
Hi, I'm Kim Hill. You're listening to Kim Hill Wants to Know, a podcast where I speak with interesting people about fascinating subjects.
Your human brain is the Rolls Royce. It's the super brain.
Distinguished Professor Sir Richard Faull has spent his career discovering the brain's secrets. You opened your first lab. What was it? Who was there? How many people? What were you doing?
There's just me.
Oh, yeah. Sir Richard is Distinguished Professor of Anatomy and Director of the Centre for Brain Research at the University of Auckland, founder and director of the Neurological Foundation's Human Brain Bank.
Now, theoretically, you can keep the brain forever.
Just over 30 years ago, 1994, he bought a minus 80-degree chest freezer, which became the cornerstone of New Zealand's only human brain bank. Sir Richard tells me how he came to be one of the world's preeminent brain scientists, I suspect to his own surprise. What I wanted to start off with was this. I was looking at the annual report,
Yep.
and the range of the involvement in the Centre for Brain Research, massive collaboration, 70 principal investigators and 40-odd community partners of all sorts of neurological disorder representatives.
Yes,
But take me back to your first lab in 1978.
Yep.
What were you doing?
Well, I'd just come back from the United States because I'd spent the 3.5 years with my wife in the United States, 1 year in San Francisco working one of the top. I was actually at a NASA base there working on the brain.
What were you doing specifically on the brain in the States?
Well, I was learning new techniques for working on the rat brain. A new set of techniques had come out called the exoplasmic transport techniques, where you could inject a dye into the brain, horseradish peroxidase, and it was taken up by the terminals and transported back to the cell bodies, and that was incredible.
Because you could see the pathways.
You could see the pathways, but most importantly, you could see the cells of origin of that pathway because it went back and marked the cells, you see.
And were you looking for anything in particular or just observing what you hadn't observed before?
Well, I was looking for the new pathways in what we call the basal ganglia, which are involved in Parkinson's and Huntington's disease. They're right in the centre of your brain, and they control, in the most wonderful way, your control of movement.
So you were already interested in neurodegenerative diseases at that point?
Yep. But I was working on the rat brain. I was looking at the pathways involved in these different types of neurodegenerative diseases, and then there's the first year in California on the NASA base. Then I went to Harvard and MIT for the last 2.5 years, and worked with the guru in the field of neuroscience. He was Mr. Neuroscience, son, a lovely Dutchman called Professor Wally Nauta, a gentleman to the core and just a lovely man. And so this is like me sitting at the steps of the master, sitting at the steps of Archimedes or whatever, just learning from and just soaking everything up, because the whole environment in Boston, it's a fertile environment. It's a crossroads, the intellectual crossroads. MIT and Harvard are the intellectual crossroads of coming from Europe into North America. So anyone who was anyone in neuroscience came to see Professor Nauta. I got to meet them.
Could you have stayed there?
I know, because I was on a Harkness Fellowship, and when it ran out after 21 months, it was actually, I did get an extension, but part of the contract of getting a Harkness Fellowship is that you would return to your own home, your own land, and you would pass your knowledge on, and that's what it was all about. And it was the most wonderful fellowship in the world and really changed my life forever.
So you got back and you opened your first lab. What was it? Who was there? How many people? What were you doing?
There's just me. So I had written a grant. On the way home, Diana and I and our little wee baby born in Boston, Rebecca, we spent 3 months travelling around the brain institutes in Europe. And I wrote a research grant up in the hills in Switzerland.
An application?
An application, yep. Sent it back to the MRC in New Zealand so that I would have money when I arrived back. And when I got back there, I was given a small grant, and it was to work on the substantia nigra and basal ganglia in the rat brain. And finding out new pathways with these techniques I'd learnt in the United States. And, you know, Kim, I was so excited. The lab was a new lab, and I had it all to myself. And I didn't have any technician, and I was just starting to teach on the nervous system, so I was learning to be a teacher, a young academic. I was a senior lecturer, as they called them.
My idea of a lab is that you've got, petri dishes and microscopes and experiments going on. So what did you have? What were you looking at?
So in the lab there would be different staining dishes and what we call a microtome for cutting. Rat brain is quite small, so when you cut up the slices to look at, you have to put it on a microtome and you freeze it down, and then you take little slices off it. And it requires quite a lot of skill to get beautiful slices.
And were these rat brains, were they normal rat brains or rat brains that you had induced into a neurodegenerative disease in some way? What?
Exactly. Some of them were normal, some of them were exactly what you said. I put a little lesion in the substantia nigra or in the striatum, and I was finding out how the pathways were connected. The pathways, especially which were involved in this stage, I was looking at the striatum and looking at the pathways which are involved with Huntington's.
When you say I put a little lesion, what is it that you put into a rat brain to examine it in that way?
Okay, you have a little electrode, make the electrode, put a glass insulation around it, and then the tip of the electrode is bare, so you bare that away with hydrofluoric acid at the time, and you put that electrode tip into the precise part of the brain which you are interested in, and you increase the current and you kill the brain cells, and the brain cells there will then degenerate, and you would trace the pathway. And also, of course, I was putting in this horseradish peroxidase to see if it would then trace back towards the cells which were projecting to the area you injected. You see.
I heard you say that before, and I was going to ask you, horseradish peroxidase.
Yeah. It's an enzyme which is just, it's a, What's
it got to do with horseradish?
Well, it's taken from the horseradish root, but it has the facility. When you buy it in especially prepared chemical lots, it has a facility of being taken up by nerve endings and carried back within the axon back to the cell body. So apart from tasting very nice on your beef or whatever,
yes,
it was a wonderful first tracer to trace connections in the brain at that time, in the 1970s.
Not to put too fine a point upon it, are these live rats that you're doing this to the brain and then you're killing them?
Yep.
All
Live
right.
rats are anaesthetised. They're put in a special stereotaxic machine so that when you put the electrode in or the injecting needle in, you read off the coordinates and you know what part of the brain you're putting it into.
Do you become irritable by people who say that we should not be experimenting on animals?
Oh, yeah. No. Absolutely. Well, interestingly, further on in my career, about 10 years after this, I was also still working on animals, but we got, the anti-vivisectionists. We got it. My wife got literally invaded at home by a whole group of them. We got paint remover poured over our car and other things going on. And, I was actually at work on a Saturday morning when this happened, and my wife went up to them. She said, "Do you know what Parkinson's is?" They didn't have a clue, of course.
Yeah.
All dressed in black. Anyway, that was another chapter.
No, it's interesting, though. I mean, for all our progress, would AI and the advancement in AI enable us not to have to experiment on live?
No. I mean, you have to look at the brain. You know, AI, for all it's a highly inflated term. It just means computers that can look at lots of big data and analyse them. It's got to have AI's got to be run by a brain. It's got to be run by a human, you know. So it's not a human. And it can't think, and it doesn't invent things, and it can't follow pathways in the brain, that's for sure.
So there you are in your lab, on your own.
Yep.
Looking at pathways in your rat brain.
Yeah. Yep.
What focused you on Huntington's disease?
Well, it was a wonderful colleague and friend, Professor Arthur Veal. He was a professor of community health at Auckland and genetics. And I had also met him in Dunedin when I was a young medical student in Dunedin. He taught me genetics down in Dunedin. Not only that, but he came from Taranaki and I came from Taranaki. And I was taught by his father at New Plymouth Boys High School. I was taught by his father chemistry. And so anyway, I'm diverging, of course. But so he comes in and he says, Richard, he says, I know you're interested in the basal ganglia. And I'm looking after all of these families throughout Aotearoa, New Zealand, with Huntington's disease. He says it's a tragic disease, as you know, and I had heard of it, but I didn't know much about it. And he said, we know it's caused by a dominant gene, so if the mum or dad have it, then each child has a 50% chance of inheriting it. He says the problem is that it can only be diagnosed by a clinical diagnosis. By looking at the symptoms of the person and then knowing the history and so on, you make a diagnosis. Once you make that diagnosis, that means that family has got the label Huntington's disease, which means they've got the gene in the family.
At that point, was it clear the difference between Huntington's and Parkinson's and,
No.
motor neuron disease? There are a whole bunch of them.
Well, the different symptoms of Huntington's disease are they could be confused with some form of Parkinson's disease. In other words, the symptoms were not absolutely characteristic. They have a chorea type movement, which is a jerky movement, which is quite characteristic of Huntington's, but they also have...
It used to be called Huntington's chorea, right? Or St. Vitus dance.
Yeah, St. Vitus dance, and it looks like the person's continuously dancing. And so he said the problem is that we don't know whether the diagnosis is really right and the families really want to know. And he said, would you be happy to look at the brains for the families when their mum or dad dies, because they want someone to look and see whether or not the characteristic degeneration is present in their brain, which is the key findings for Huntington's disease. You can tell by slicing the brain up and taking little sections whether or not the person had Huntington's or Parkinson's disease. You can tell.
And on from that, you needed a way to diagnose it while people were alive, rather than having to do the autopsy.
Later on, of course, in 1993, when the gene was found, you can test genetically and so on. So, and also, we learned more about the symptoms of the disease and all the rest of it. So it's become much more refined.
Who found the gene?
Well, there's a big collaborative research group. There were people from the UK and from the United States working together under a wonderful woman called Nancy Wexler, whose family had Huntington's disease. And they went off and there was a big family in Venezuela, in Lake Maracaibo there, an extended family where Huntington's was rife because there'd been a lot of intermarriage. And so they went down and collected this big team. And one of the people in the team actually who was involved with the scientific analysis of it was Russell Snell, who I'll come back to in a moment, a New Zealander doing his PhD in Wales. So they collected the bloods in rather complicated analyses, which I don't fully understand, but they were able to after 10 years, they were able to do research and they actually found out exactly what the gene was. And they published a paper in 1993 showing that the gene was what they call an expanded repeat, a CAG repeat. And that was marvellous. Now, Russell Snell, he's now a professor at University of Auckland, works in our Centre for Brain Research, one of my wonderful colleagues. He was part of the big team that worked between basically Harvard University and universities in Wales to unravel this gene.
So finding the gene was obviously massive, because then you've got the ability to find out whether someone is going to develop it or not.
Exactly.
But of course the downside of that is that you can't do anything about it.
No,
or can you?
Not yet. We can't do anything about it yet, but the latest research is trying to see if we can turn down the gene, if we can silence the gene, or we do know it interacts with lots of other genes now. So there's lots of exciting genetic research looking at see if we can alter the actual activity of the gene so that we can offer these people, if they have the gene, we can offer them hope for the future. So
why isn't it easier than that? I mean, why isn't that immediately possible? You've got the gene. We know how to do gene therapy. You've got Professor Chris Shaw spending a lot of time here. He's a gene therapy expert. Why don't you just use CRISPR on that gene?
Well, the problem is that, and I'm not a geneticist, so I can't give you all the intricacies, but the problem is that you have to specifically be able to turn down just the mutated gene and not the normal gene. That's one thing, because people usually it's a dominant gene, so people often have a normal copy and a mutated copy, and that can have all sorts of other side effects. But the hardest thing is to get these little what they call
the nucleotides.
Antisense ASOs, antisense oligonucleotides into the brain to the right spot, and that is not easy. So there's huge technical problems, and people are working on it from all directions now. So it's not a straightforward procedure. They've done trials, and they thought they had a great antisense oligonucleotide, but didn't actually get into the brain. So that was not helpful, but they're pursuing other alternatives right now, which I would think in come 5 to 10 years' time, we will be able to offer families enormous hope who have this gene.
I mean, you worked very closely with families afflicted by Huntington's disease, and it's a terrible thing, as you say. You know, it's hereditary, and your children have a 50-50 chance of getting it, and it will kill you, and it is incurable. Do they get impatient with you? I mean, I know you're very careful not to offer false hope, but do they say, after all this time, can you not do something?
Well, they started me on this whole line of research of looking at the human brain because, of course, when they gave the brain to us to find out whether or not their mum or dad died of Huntington's, in 1981 when we got the first brain, they said, well, keep the brain and do research on it. So that changed me from the rat brain to the human brain. And so over the years, I've just gradually shifted more and more to the human brain, but we still have groups which work on the rat brain. So we ended up establishing very close relationships with the families, because to give the brain of your mum or dad when they die to research is, it's the most wonderful thing in the world. It's a gift. We are the custodians of their mum or dad. You see, we don't own the brain. The brain still belongs to the whānau, the family. And so we always report back exactly what we find and give them all the details. But more than that, we found that when we looked at the brain of different people with Huntington's disease, there was such a variation in the pattern of cell death between one brain and the next. To me, this just didn't make sense, because everyone had been saying the pattern of cell degeneration was very homogeneous. It just followed these steps. These areas were involved, but the areas were involved in quite different ways, the parts of the basal ganglia. And only until I talked to one of my close colleagues, Lynette Tippett, who was a psychologist, he said, we need to go and get all the history from the family. So we went back to all the families. She sent all her graduate students out and collected the precise history, the life journey of the persons whose brain we looked at.
And how the disease manifested itself stage by stage.
Exactly how it started. What were the pattern of symptoms? Was it mainly movement, or what types of movement, or was it not so much movement, but mainly cognitive changes in different types of mood?
And so, could you match that description of the disease's progress with what you observed in the cell death in the brain?
Well, you've hit the nail right on the head. I didn't realise that by collecting that information on each brain and knowing the pattern of cell death, we were in a way doing a reverse to what people did in animals. In other words, when you do animal studies, you put a little lesion in, you knock out a few cells, see what it does to the animal, and then you work out what that area does, right? Well, we were looking at the brain after people's lives and matching up their symptom development with what we saw in terms of the brain cell death. And so we were able to utilise that to work out what the different compartments and the different groups of cells were doing in the basal ganglia. Now, this was revolutionary.
Because you could see which cells affected the motor and which cells affected the mood, for example.
Exactly.
Did you not know that before?
No.
And is it always the same cells in each person's brain? Like brains don't have, in terms of their physiology and what the neurons do, they don't vary much. Or do they?
Yeah, well, there is actually a variation between what we call the interneurons and the cortex, but just to take this a step further, since you're prompting me and give me an opportunity to do this, which is incredible, we found that not only were basal ganglia cells dying, but we found that cells in the cortex, that wonderful outside of the human brain, that folded part of the human brain, which everyone, sees in pictures and so on.
The walnut bit.
The walnut, yeah. So cells were dying there, and in different patterns again. Now, the cerebral cortex is it's the icing on the human brain because it makes us different to all the other animals. We are what our forebrain and cerebral cortex is. We have a large folded cerebral cortex because we're behaviourally quite complicated people. Oh, don't get me started. So what we found, you see, Kim, and I hope you get the excitement of this, is that we were finding, and I had another set of half a dozen PhD students looking at all the parts of the cortex in these different brains with different symptoms, and we were unravelling the functional organisation of not only the basal ganglia, but of the cerebral cortex. Now, you can't do that on an animal brain because a rat's brain is a little wee, it is about, 2 centimetres long. Your human brain is the Rolls Royce. It's the super brain.
And so it was inevitable that your study of the brains of people with Huntington's would also feed into your study of people with other neurological disorders.
Exactly. Well, yeah, you've hit the button on the head. So as we were seeing what we could find out about Huntington's, we then started collecting brains from whānau families whose loved one died with Parkinson's disease. And we found the same things happening there, that there was a lot of variation between brains. There's not, Parkinson's isn't just one disease. It is a myriad of different variations. In fact, no one brain disease is exactly the same as from one person to the next. It varies. And it varies according to their symptom profile, all the rest of it. So when you look at a patient in person with a brain disease, they are telling you by their symptom profile and by the way they look at you, you're seeing the outer manifestations of what's going on in the human brain. And of course, by then looking at the human brain, you work it in reverse. So, little old Kiwis, scientists down here, we've become world leaders in the human brain and what happens in these different types of diseases. Why have we become world leaders? Because families have given the brain to us, but not only that, because we would feed the results and tell the families what we found and often had to get more information from them, they became part of our research team. And I'd go out we'd go out and do lectures and just update them to the different associations, telling them what we were finding. And in a small country, you can do that. So we ended up as a network. So the families whose brains we have, they are as much part of the Centre for Brain Research as what the scientists are. And not only that, because they gave us permission to talk to the doctors and neurosurgeons who may have operated on the brains and have information about the history. They gave us permission to access that. So we were beginning to set up what I call the Holy Trinity of brain research. The scientists in the university, the patients and families in the community, and the doctors and neurologists, neurosurgeons in the hospitals, 3 pillars. But this was set up slowly over 40-odd years. If I can just go back one step, as we were collecting the brains from first Huntington's, second Parkinson's, then Alzheimer's, motor neurone disease, frontotemporal dementia, we were gradually getting more and more brain tissue stored in our freezers with the custodians of the brains for the families. And it occurred to me in 1993, I thought, my God, we've got an incredible bank of human brains here. Why was it incredible? Because when the families realised that to do really good research, we needed to get the brains soon after death as possible, then they worked with us. They would notify us in advance, the week before, the day before, whatever, when their loved one was declining, so that we could receive the brain as soon after death as possible. So that was a real partnership. And then, of course, we'd feed the results back to them. So we had tissue, which was first, we received it very soon after death, within 2, 3, 4, up to 10 hours, 12 hours or so. And so it was high-quality tissue for research. Brain banks in the United States and around the world, they have a lot longer interval between death and when they receive the tissue, often days.
Because they're just larger, more complicated.
Yeah, larger, it's a bigger country.
Right.
But we were doing it the Kiwi way. We were working, we know all the families who've contributed brains to us and we keep in contact with. The other thing, of course, is that they were giving us the secrets to their mum's brain. They were giving us the history, the life of their mum or dad. Now, that doesn't happen in the United States where they've got the big New York brain bank. The brains are stored as either Parkinson's brains, Huntington's brains, motor neurone. They are stored without this exhaustive clinical information. So we were collecting information which was invaluable. So in 1993, just after I graduated in medicine, I didn't know whether I was going to do neurosurgery or actually brain research. So I spent some time in neurosurgery and I got to know the neurosurgeons really well. And one of the young neurosurgeons then in 1971, well, he wasn't so young, but it was Philip Wrightson, a wonderful guy who's also the medical director of the Neurological Foundation. So I go and see Philip. I said to Philip, we've got these brains here. We work on beautiful human brains. We have to put a lot of work into processing them. And I think, we've got a human brain bank. And I said, now, you're the medical director of the Neurological Foundation. You have money to support research. Would you perhaps fund a person to help us run the brain bank so we don't have to use all our research funds to just look after all the brains? And if the Neurological Foundation are happy to do that, we would then call it the Neurological Foundation of New Zealand Human Brain Bank. So he goes off to the council, and then, to cut a long story shorter, they said yes. So we got our first post, and from then, in 1994, we had the New Zealand Neurological Foundation Human Brain Bank, although we'd been going for, 15 years up until then anyway.
Right.
And so over the years, we have expanded this relationship. My life's an unexpected journey.
Do these brains last forever?
Well, look, over the years, we have developed superb processes for cutting the brain into very small blocks from all the different functional areas. One half of the brain, we cut the brain in half when we receive it, and one half is kept fresh. That means you can do all sorts of chemical and gene studies on it later on. And the other half is what we call perfused with formalin, which fixes the brain for all sorts of other techniques. And so we've got ourselves covered with all the different techniques you can use for research. And so each side of the brain makes about 60 blocks. And we carefully, with the most greatest respect in the world, because this is like handling a treasure trove, The human brain's a treasure trove for the family, for the person whose brain it is, and for us in research. And so we carefully have developed techniques so that we don't waste any brain, and we block them down. They're all coded, and then they're processed. All these blocks are processed, and then we freeze them down, and they kept carefully wrapped up, each block carefully wrapped up in a double layer of tin foil, in the freezer at minus 80 degrees. Now, theoretically, you can keep the brain forever. And because it's minus 80, you see. And then we take a block out. We need a little bit of this tissue we need, say, 10 Huntington's brains to do this, to look at this thing, this possibility of brain cell death or chemical change or gene change or whatever. And we take little slices off it and put it back in the freezer. So it's our encyclopedia of human brain tissue. And so we just had our 30th anniversary with the Neurological Foundation for the Brain Bank. We commonly refer to us as the best little brain bank in the world. And what happens when you go and talk at overseas conferences and you start telling them, this is in the early days, you start telling them what we're finding from the human brain, people get jealous. Scientists think, you work on this human brain tissue and you found this out and you know all this about, gosh, we've got brain banks over here, but they're not like yours.
Because you're looking at the living witnesses to the people whose brains you have.
And we have all this history on it. You see, it's not just a Parkinson's brain or a Huntington's brain. It's a brain from a person who had this pattern of behavioural symptoms.
Do you think this is a function not only of our small country, but also because of your determination to involve Māori and therefore to apply Māori tikanga to the way you investigated this?
I think what you're saying to me is that because I'm Māori, I didn't realise it. I didn't attach too much to the fact that I had a Māori whakapapa at that stage. But we were collecting tissue in a way and using it for research and working with Māori and observing tikanga principles. We had Māori donors. We don't have a lot of them, but we have Māori donors, and we use that tissue with the proper respect. The tikanga, they come in. The whānau come in if they want to, say karakira over the freezer and so on. I mean, all this is part of it. But whether it was a Māori brain or a Pākehā brain, the emphasis was with the ultimate respect. This is almost it's difficult for me to describe the respect we have for the human brain tissue. The families know that. They come in, we show them around, we show them where the brains are stored, whether the Māori or Pākehā. But I was actually unconsciously working, and I had, because of my Māori whakapapa, I didn't realise it until the last 10 years that I was actually doing and handling this tissue in a way which was consistent with Māori tikanga.
I'm surprised to hear you say you don't have very many Māori brains because you put such a lot of effort into reach out. 28, I think, iwi affiliations and many visits to marae. Why do you do that?
Can I give you a little story? When I went overseas, you see, and worked and did my postdoc studies in the United States, and Dinah and we wanted to stay a bit more time at Harvard to finish learning these new techniques at MIT. And so but we were running out of money from the fellowship. So I wrote home to my dad, and I said, "Oh, Dad, we need a bit more money," and not expecting him to go and find it for me, but just saying we'd love to stay a bit longer. Well, he just happened to talk to some of our kamatua, Te Atiawa kamatua in Taranaki, as people in Waitora and Tikarangi, where I came from, and they said, we'll give him $1,000. And so Dad wrote back and said, the Taranaki Maori Trust Board want to give you $1,000 to help your research. Well, I was aware of Maori whakapapa and so on, but, I didn't speak te reo, I hadn't grown up on a marae, we'd never even been to our local marae, Owai marae. We'd just grown up in a Māori community and we loved everyone. So I wrote back and said, Dad, I don't think I can take this because I don't feel Māori. And so he went back and talked to the kamatua, and then he wrote back. They said that's not a problem. He said, they have told me that one day you will come home. And so I didn't realise that was going to take me probably 20 or 30 years to properly come home. When we started developing our research, I'd always go down to Taranaki and talk to the community groups about our brain research studies on Parkinson's and Huntington's and so on. And one of the visits, this was I think 2003 or so, there was a group, and I was down talking about Parkinson's and a little bit about Huntington's, and at the race course there, wonderful place, and they were very interested in what was going on. And there's a group of Māori just standing just at the back. And so when I came, I went, as I always like to go around and say hello to everyone before we start, before I give a lecture or talk to people. So you get the feel of the dynamics of the place. You see, they get the feel of you, and they suddenly realise that I've only got one head, and that I'm a scientist and I'm no different to them really. And so you establish a bit of a relationship before the lecture, and then afterwards, after lecture, I went down and talked to them again. They said, we've got a big problem in our family, in our whānau. We've got Huntington's disease. Will you come and help us? And I realised later down the line, these were people from my own iwi. They were Te Atiawa. And so I said, of course I'll come down and help you. Well, from that time on, I've gone down, I take Kuia, the wonderful Dr. Waiora Port and other Māori colleagues with me, and we go down and we see that's this extended whānau, at least once a year, sometimes two or three times a year. We are really part of their whānau, and we just tell them where research is going, and we make sure they get good clinical support and all the rest of it. So you see, I was beginning to come home properly. And then when I found this was so effective over recent years, and I realised how important it was that we take our research to all the people, not just to Pākehā, but I must go to Māori. So we appointed a Deputy Director Māori, Dr. Makarina Dudley, a couple of years ago, and she comes from up north. And she has taken us to Marae because she's an expert in dementia, and she's rewritten the book on dementia for Māori, written in te reo. And so instead of, Māori won't come into a medical school and sit in the lecture room because it's foreign territory. So what I say, we should get off our bums, go out, go onto the marae, we may feel uncomfortable, and we'll talk to them. Not only talk to them and tell them what's happening with these different diseases, but listen to them and see what their problems are. And although we can't cure their disease right now, we can provide a level of care and support by helping them to apply the best ways of how to look after people as they suffer from these different diseases. So, over the last 3 years or so, we have visited 15 marae from Kaitaia in the north all the way down to Invercargill. But it's just gone in a stepwise fashion. And so this is my whakapapa working through me. This is my tikanga Māori, you see.
I've heard it said that Maoris suffer from higher rates of dementia, in part possibly because they suffer from higher rates of diabetes, for example.
Yep.
Why would one lead to the other?
It's not just Maori with diabetes, of course, it's all people with diabetes.
Sure.
I'll come back to that in a moment. So your brain is operating right now because every time your heart beats, although your brain's only 1,500 grams or around about that, in other words, about 2% of your body weight, every time your heart beats, 25% of the output from your heart goes straight to the brain. So your brain is so critical to you that the heart is married to the brain. It gives it a disproportionately large amount of blood compared to its body weight.
And thus it is disproportionately dependent on the health of the rest of you.
Exactly.
Right.
And especially the blood vessels. I mean, and diabetes, it causes hardening of the arteries, causes atheroma. And so with the vessels going up to your brain, when they become affected by the disease, the side effects of diabetes, if you like, then you're getting less blood supply to different areas. So you can get what's called a vascular dementia, a dementia which is caused through the deprivation of blood due to blood vessel disease.
Right, and that's vascular dementia, which is different from Alzheimer's.
Yeah, well, it's different from Alzheimer's, but nevertheless it does play a part in Alzheimer's too.
Does it? Because I'm thinking all these neurological diseases that you study, they all seem to, correct me if I'm wrong, have in common a rogue protein caused by some gene malfunction or mutation.
Yep, you're right, you did right.
And so if dementia is dependent on other parts of the body, where does the rogue protein come in? Are you suggesting that a healthy body might prevent that protein from settling in?
Well, you should have been a scientist, Kim.
There is yet time.
There is plenty of time. So different neurological disease, different neurodegenerative diseases like Alzheimer's caused by tau protein, that's a rogue protein. Huntington's is what we call the Huntington protein, and synuclein is one involved with Parkinson's and so on. Yes, you get bad proteins, but in addition, if you are diabetic or if you're obese and don't do much exercise, and if you smoke and if you have high blood pressure, then all these things affect your heart health and your blood vessel health, and that will be over and above what's happening on with your different types of neurological diseases caused by these bad proteins. So you see, there's no such thing as a pure disease in life.
No. And while there is nothing, as I understand it, you can do to stave off Huntington's, you imagine that there is something you can do to stave off Alzheimer's. Do you think?
We know the risk factors which will predispose you. These are modifiable risk factors which, if you can minimise them, will actually work in your favour and slow down the progression and the onset of Alzheimer's. So if you get your high blood pressure treated, that'll be great. If you stop smoking, if you get diabetes treated, if you keep yourself nice and trim and do exercise and are not obese, obesity is an anchor which will take you to the grave. All right? So high
How
alcohol.
do you feel about, there's a wave of people saying, don't fat shame, The fact that you are overweight doesn't mean you're unhealthy. You can be obese and healthy.
That's nonsense, actually. It's straight nonsense because it's just not supported by the evidence.
Because this is the other thing, as we become increasingly overweight as a society, we're going to get more and more of these diseases evidencing themselves.
That is exactly, that's so true, so true. Just having a balanced diet, had that glass of wine, that's nice, but don't drink the whole bottle. If you've got a hearing loss, get it treated, as I have. Diana and I have just got hearing aids.
What's hearing loss got to do with it?
Well, it's just, you see, why does your brain stay healthy, Kim? It's because you keep socially interacting. You are talking and interacting with people. That's one thing. Which is, the more you socialise and you interact with people, the better your brain. This is getting sensory input. So your brain is only a healthy brain if you get all those sensations feeding your brain.
So if you are deaf or partially deaf, it's in a way a sensory deprivation.
Exactly. And it's sight's the same thing, and so on, because the human brain feeds on social interaction with other people. All the fun things in life are interacting. When you get your family together, whānau together, when you have parties. I mean, why? We feel good. And when you play games and that, which is socially interacting, all the different sports, it's social interaction.
You're talking to an introvert here, Richard. I'm getting depressed.
Oh, yeah, you're not too much of an introvert of all the people you talk to.
Seriously, an introvert.
Well,
that would be an interesting study, right?
Yeah,
whether introverts have a higher rate of neurological illness than others.
I think you're doing yourself a little disservice here, because what's great about being an introvert is that you focus. You see, you focus on something. And you are a ferret. You will follow.
I've been called nicer things.
Well, I mean, I meant it in the nicest possible way.
How do you keep your brain healthy? I mean, apart from, you say, the hearing aids, and you're clearly a sociable person. You like people. You enjoy stimulation, and you live a fairly healthy lifestyle. Is that it?
Well, pretty well, yeah. But, I do love cheese. I love blue cheese. And I try and have it now in moderation. I'll tell you what, I can't stand jogging, so I can't jog and exercise. But what I do like is walk, and I try and walk each weekend. On average, my dream is to try and walk about 4 Ks a day. Well, I can't do that during the week because I'm working. But in the weekend, I can walk 4, 5, 6 Ks. And you meet lots of people walking. I mean, up our mountain at Mount Albert and Oraka. I mean, it's wonderful.
Have you got a dog?
Yeah, well, I don't have the dog, but we used to have a dog, but my daughter's got a dog, and dogs are good for you.
Dogs are good.
Yeah, but I can't.
Dogs can do the socialisation.
Oh, yeah. But I grew up on a farm, and dogs are supposed to work, so anyway. So how do we get on to this?
Well, we all know of people who have kept their brains healthy, and they've been stimulated and clever and intelligent and sociable, and they've still succumbed to some neurodegenerative Parkinson's.
We don't know how much that all of these activities actually slowed it down. You see, studies have been undertaken which show that if you addressed all the risk factors for Alzheimer's, that will push out the onset of these diseases, neurological diseases, especially dementia. So
you might die before it sets in.
Exactly.
Right.
That's right. So if you keep my theory is, and it's a purely optimistic theory,
yes.
The more you keep pushing it out, you'll die of something else.
Yes.
But you'll live much longer, more switched on, enjoy life, and just go for it. But in the final analysis, it's not how long you live, it's what you do with your life that counts,
One of the other things that you found was the plasticity of brains, that brains carry on producing new cells. They can repair themselves, or at least attempt to.
Yeah, exactly.
Can they repair themselves? Well, I don't know. I was going to say, can they repair themselves successfully, but how would we know?
What we found, and this is because we were looking at human brains and the brains in Huntington's disease, this is the work of Maurice Curtis working with me as a young PhD student, and we found in Huntington's brains that there was increased numbers of brain cells right next door to the ventricle, which in the rat we knew were where the rat had stem cells left over from the embryo. And to cut a huge long story short, what we ended up showing was that there were still stem cells in the human brain left over from when you were young, and these are what we call them adult stem cells, and that they can produce new brain cells, and they go down a pathway around towards the olfactory bulb, and they can reach out to other parts. So you can make new brain cells forever, but of course, this pathway is working overtime when you're young, when you're developing your brain, but it does fall off later. But we don't know the propensity of what sort of contribution it makes as you get older. Probably not a lot, but the fact is that property is there. But there's another side to this plasticity, And that is that in addition to making new brain cells, now we've been talking now, and you may have learned one or two new facts, I don't know, hopefully at least one. That means your brain's changed, right? And that means...
only if I remember.
Yeah, only if you remember. Well, even if you don't... But the thing is, your brain is changing. So your brain is changing every single day of your life, every second, because you're getting a new experience. I came in here to Radio New Zealand. I mean, a young guy at the counter looked after me and all the rest of it, and so on. So you're interacting, and your brain was being stimulated. And we know that when your brain is being stimulated, what happens is that we're not sure how this changes your brain in toto, but we do know that all of our neurons that have dendrites and so on, that the more you stimulate the input to brain cells, then they will change and develop, and they will actually store new knowledge, they will remember the past and so on. So your whole brain is, and we send kids to school so they learn things, so they're storing. So our brains are going on forever. So the idea that we have a plastic brain, when people thought about it, it's so obvious, isn't it? It's so obvious that our brains are changing, and it changes at every level. It changes at the level of the branches of the dendrites. We know that from animal studies. It changes at the level of gene expression inside each brain cell. It is dynamic.
Can you imagine then that we might find a way to stimulate the brain to produce more and more stem cells to repair itself better?
That would be good, but they've got to make the right type of brain cell.
But I thought stem cells could turn into the right kind of brain cell.
Well, theoretically they can, and so all of these activities, exercise, all the rest of it, we know in animals that make new brain cells, so we can't measure it in humans, but I believe they are actually making new brain cells, and it's good for you. So, and the answer to your question is, in a general term, yes. And it's a good story, and so go with it.
Yeah. But, I mean, you're obviously afraid of over-promising, gene therapy, stem cell therapy. It was, both of them were the great hopes for a while, and then it seemed to become more complicated.
Hugely complicated, and transplanting stem cells it's known that that's not going to really work. But, when you just come down to the basics, what is good brain health? Well, good brain health is doing what you love, working with the people you love. So it's social interaction, looking after people. I mean, when we had these different disasters over the years, and you see whole communities come together and doing things. I mean, I grew up in a little farming area, and Mum and Dad had the shop, and life then, in the 1960s and 50s and so on, was all about looking after everyone because we had to in order to survive. And there's a huge community spirit there. So community spirits, we need to reinvent community spirits in the big cities. But it's always these challenges in life which bring people together because we are basically social animals, and we actually care about each other. And some people make it more obvious than others. And so part of my job at work each day, I don't like sitting in behind a computer and just interacting with the computer all day. It drives me absolutely nuts. So I go around and I talk to, especially our early career research, our young people. At first it keeps me young, but secondly, they'll come up with ideas and suggestions on how we can do it, and how we can work together, how we can collaborate together better. So my job is it's an open. I run my life as an open door. I don't a closed door. And the power of collaboration on people working together, and this is what the secret of the Centre for Brain Research are. All we've done is actually identified and got people doing brain research across the University of Auckland. We started in 2009 with 25 groups, and now we've got 92 groups, a part of the centre. And it's all about collaboration, working together, geneticists working with the pathologists and psychologists and artists and, people in dance and all the rest of it. And so having a virtual centre which just promotes collaboration is very, very powerful.
You've created your own scientific and non-scientific community.
It's a little army, you know?
Yeah.
And also people can see, well, it all came out of the human tissue because, of course, we need the geneticists to look at the human tissue. We need the people doing physiology and pharmacology, and we can, and what we haven't even touched on here, I mean, we know that we can take slices of the human tissue soon after we get it, and if we get it straight off the neurosurgery table with the patient's consent, we can take it into the lab, we can dissociate the brain cells with special enzymes and keep the human cells alive and ask them questions. If it's from a person who's got a brain tumour, we can trial drugs against them in the dish to see what's going to stop that cancer growing. And it brings us closer to the neurosurgeons, and they're now working in our centre, they're part of our centre, same as the neurologists are. So it's about working together for the common good. It's not rocket science, but it's
Not
powerful.
rocket science. I wanted to ask you whether you welcomed the moves to ease restrictions on genetic modification and gene editing.
Yeah, we've got to use gene technology, you know, to try and solve all our disease. I mean, the actual argument against it doesn't hold water, really.
So will you be able to do things, or
Yep.
will Professor Shaw, Chris Shaw, who's running the
and Debbie Young and Russell Snell.
They'll be able to do things now or will be able to do things if this goes through that they couldn't do before?
Yep. And you know, so another project we're doing is looking at people with autism, and some of that's genetically based. So we've got to go and we've got to use every type of bullet in the bank in order to help people's lives. And we're not changing the genome. I mean, the person is still the person, and we're just doing what, in fact, you know, nature has done in different ways and all sorts of things.
I know you've got a whole bunch of sheep in South Australia.
That's right. Absolutely. So
transgenic sheep. You couldn't have them here, presumably. That's why they're in Australia.
In the early days when we first, and this was Russell Snell's idea, was to take the human Huntington's gene and put it into the sheep, and then if you can replicate the disease, you can trial new therapies to actually switch or slow the gene down. That's in the general theme. Well, it was at a time when there was so much sensitivity here. We could have done it here, but it was too hard. And in Australia, there's a big SARDI, it's the South Australian Research Development Institute in Adelaide, a big government research station, and they routinely, they have a big flock of sheep, there's 6,000 acres, they've got them on, and they routinely put human genes for any type of disease into sheep. So when we found that out, that was a natural association, so we have continued to work with them, not only making a Huntington's sheep, but also now Russell's got he's got 2 lines with the different genes which are suspect to cause Alzheimer's disease, and it's really going incredible. So these, and you know, that was funded by the Freemasons because, in fact, they gave us money because this was dream research, and you can't get funded from our government for dream research.
Is that another way of saying blue sky?
Blue sky, absolutely. Right. Yeah, and you've got to, I mean, to be a proper scientist, you've got to dream, and you dream hard, and never give up on a dream. So that's why we developed the association with Australia, and through that association with other scientists around the world who also were interested in these animals. So the wonderful thing about Kiwis is that we collaborate easily with the rest of the world, and also...
Do you think that's because we're not threatening?
Yep, exactly. I mean, it's interesting. So when we started talking about some of the results of our human brain studies, and we got different groups from overseas asking us if they could use some of the tissue, so we go back to the families and say, would you be happy for some of Mum's brain to go to this group in Boston or that group in Zurich or Gothenburg or whatever? Every single case, the families were ecstatic. They say, you know, things like, it's like
Mum always wanted to go to Gothenburg.
Yeah, well, Mum's getting the travel in life, and Dad's getting life, or Dad's brain lives forever, helping our kids. So they think it's wonderful, and also it gives us natural collaboration. So we can collaborate with the best in the world. And some of the groups we collaborate with, especially in North America, they won't collaborate with each other, but they collaborate with us, you see. And we just got to embrace science, use it in an ethical and an appropriate way, keep people informed. And often, when you get people going against you, it's because we haven't explained it enough. We haven't actually gone out there and explained it, and we need to do that. So communication is key. Absolutely key. Talk to people. Tell them. That's why going onto a marae and telling people and taking with Makarena Dudley, and we go out and we find out that, in fact, the way they look after their kamata, well, they don't even have a word for dementia. They just saw it as a natural progress of people transitioning when they get older.
Maybe it is.
And maybe it is. And
do you think it is?
But, well, it depends on your philosophical point of view. I mean,
it's a pretty rough transition.
Yeah, it's not a transition we want. But what I was trying to come round to was that we have found that the way they care and look after their elders, their kamata, is the way we should all be doing it. Looking after them in a caring, loving environment. They teach us so much. So we actually are helping to support their carers, who are helping to support their people with what we call mate wariwari. That's the term we now use for dementia with Māori.
Mate wariwari.
Mate wariwari.
Let me ask you this: as we're talking more and more about categories of people, people who suffer from ADHD or anxiety or depression or autism. Is there a danger in reducing personality to brain cells and neurons?
I think I know exactly what you're saying. The answer is yes. We are all on a spectrum. And so we should, who wants to be exactly the same? And so the diversity and the great strength of the human race is that we are all different. And some people are a bit more different. Some people may be highly intelligent, may be autistic or whatever, and finding what unlocks their brain so they can get their full potential. That's the challenge in life. And looking after people and, having a single education system, which is not going to, everyone's going to learn a different way. So we've got to make sure that we embrace flexible methods to look after the great diversity of people, all ethnicities. And when you look at the state of the world today, you think, gosh, have we really advanced? We've got all this technology now, but do people really enjoy life as much as what my mum and dad did, as what they did in the Roman times or whatever? Because we seem to be making a bit of a mess of it.
Do you think we are making a mess of it?
No, I don't think so. But I think it's just we get too much of that negative publicity, which sells the news. But we need to keep highlighting what are the good things in life. They do come through. When you look at communities and the way they rise to the occasion, they all, over COVID, look at the way the place came together.
Yeah, but then we all turn nasty.
Yeah.
Let me ask you this. I think there is some evidence that there is a genetic basis to Alzheimer's that you can test for.
Yep.
Have you been tested?
No, well, no, I haven't
Would
been
you be
tested.
tested?
But there's a whole variety of genes, you see.
Yes.
And what we can do now, we can do whole genome scans, and that shows, so genes don't work. We got 45,000 genes in each of your cells in your body, in your brain, everywhere. And you see, they all work together in different ways to make different types of cells, and their normal function. All the genes interact. They don't work by themselves, you see. So gene-gene interaction is very complex, and so one gene, although in Huntington's disease we have one gene which, if it shows a particular mutation, you'll get Huntington's disease. But we've found over recent years that there's about 25 or so other genes which modulate that Huntington's disease. Some make it worse. Some make it express the bad protein a lot faster. Some will suppress it.
Oh, it's too complicated.
Yeah, but so what we're trying to do now is work through all these other gene-gene interactions, and it does get very complicated, but life is complicated. But nevertheless, it gives you more bullets in your arsenal to help people and give them a quality of life. We're not going to completely cure everything, because otherwise we're not going to live forever. But we need to have quality of life as much as we can.
We've all got to die of something.
Yeah, but enjoy life while you can, and that's really so important. But never forget that it's when it all comes down to it, it's about looking after the people and making sure when you talk and interact with someone that they feel better for interacting with you. You know, if we just did that, Mum and Dad told us that in our general store, you know, just look after, people would come in, little country area, and my mum was the marriage counsellor for the district, you know, so very interesting.
Crikey, that would have been a hard job in a small town.
Well, she loved it because you get a cup of coffee, get a fag, go into the back room and they'll have a good talk, you know. And but she was just an anchor for the community. You know, she shouldn't have been smoking.
She would have known a few secrets.
Yes. But did she enjoy life? She loved life.
Well, you've brought a ray of sunshine into my life today, so thank you.
Oh, it's a pleasure. Absolute pleasure. Thank you, Kim.
Thank you for listening to Kim Hill Wants to Know, hosted by me, fairly obviously, Kim Hill. Kim Hill Wants to Know is produced by Melanie Phipps, with help from Liz Garton and Brianna Uratich-Gregg. Graphics were designed by Robert Whittaker, and the original theme music was composed by the Phoenix Foundation. Particular thanks to RNZ's audio engineers, who've made everything sound, well, beautiful. Follow and listen on Apple Podcasts, Spotify, or any podcast app so you don't miss an episode.